We want to look at common continuous random variables, starting with exponential random variable. Now, first we'll look at the notation for an exponential random variable. So so here we have one parameter lambda. So we say that x is an exponential random variable with parameter lambda, where lambda is greater than 0. Now the PDF for this exponential random variable will take this form. Fx of x is equal to lambda e minus lambda x, where x is greater than equal to 0, where we know lambda is the parameter of the exponential random variable. And so since the PDF is non-zero for x greater than equal to 0, so we know this exponential random variable takes all values greater than equal to 0. Because we know a continuous random variable takes on values where its PDF is non-zero. Because wherever the PDF is 0, when you integrate the PDF over that interval, the area under the PDF would be 0, which gives us the probability the continuous random variable lies inside the interval. So just remember, for any continuous random variable, it takes on values where its PDF is non-zero. Since an exponential random variable's PDF is non-zero for x greater than equal to 0, so an exponential random variable takes on values greater than equal to 0, and this is how we can plot its PDF as well. So this is the PDF of an exponential random variable x, which is the parameter lambda. Now, we can also derive an expression for the CDF of an exponential random variable. When we derive it, we get 1 minus e minus lambda x for x greater than equal to 0 and 0 otherwise, right? So we have a nice closed form expression of the CDF of our exponential random variable. Now, so this basically brings us that to find any probability involving an exponential random variable, there are two things we could do. The first is we could integrate the PDF, because we know area under PDF for a continuous random variable gives us the probability the continuous random variable lies inside the interval, and we know the PDF of an exponential random variable x with parameter lambda is this. How does an approach to? We can use the derived closed form expression of CDF. So we know, okay, we found the CDF as this. If x of x is 1 minus e minus lambda x, where x greater than equal to 0 and 0 otherwise. So we can use this expression because we know this gives us probability x is less than equal to x. So if you want to find any probability that's not the form probability x is less than equal to x for an exponential random variable, so that's just the definition we see here. If you want to find probability x is greater than x, then we know we can just do 1 minus capital F x of x, because by using the complement rule, because you know capital F x of x is just probability x is less than equal to x. If you want to find the probability x lies between a and b, then it can just be capital F x of b minus f x of a. So this is in detail in how to find probability of any continuous random variable using PDF or CDF. Right, so just like for any other continuous random variable, for exponential random variable, you have two options when you want to find any probability. You either integrate its PDF or use the derived closed form expression of the CDF that we found, right? Now we also have derived forms of expected value invariance exponential random variable. If you find the expected value for x, it turns out to be 1 by lambda, and variance turns out to be 1 by lambda as well. So if we know that we have an exponential random variable and we want to look at its expected value invariance, then we can just simply then unless it's asked, we don't have to derive it from scratch unless the question specifically asks you to do that. You can just use the fact that we know for an exponential random variable with parameter lambda, expected value of x is 1 by lambda, variance is 1 by lambda square. So then we move on to Memmile's property of exponential random variable. Now, exponential random variable is the only continuous random variable with Memmile's property. Just like geometric random variable is the only discrete random variable with Memmile's property. Now, the Memmile's property says the probability x is greater than s given x is greater than t is just simply probability x is greater than s minus t. So now this allows us to write a conditional so this basically allows us to write any conditional probability involving an exponential random variable in the form of an unconditional probability. So this allows us to write a conditional probability of the form probability x is greater than s given x is greater than t in the form of an unconditional probability x is greater than s minus t. So that is how the Memmile's property here is helpful, because given a conditional probability of this particular form, right, in the specific form, if you have a conditional probability, then you can write it in the form of this unconditional probability. Now, let's look at an application of exponential random variable. It's a good model for many time until scenarios, which means, you're looking at the waiting time until something happens. Like it could be time until your turn comes up. It could be time until 37 data packets arrive. It could be time until an electronic component fails. So it's a good model for many time until scenarios where you're focusing on the waiting time until something happens.